Hi folks, Mr. Ackerman here. Thanks for watching. The topic of today's video is momentum and impulse. We're starting a new unit here, and the topic, momentum, you've probably heard of before. You may have used it in your vocabulary just in regular conversation, but you may not have ever really known what exactly it means from a physics standpoint. Well, momentum is a really important concept in physics, especially when you're talking about collisions. And if you think about it, collisions are extremely important to understand because things happen when collisions occur. Think about, for example, when two atoms or molecules collide, new chemicals can form. That's extremely important on the microscopic scale. Think of sporting events like football or hockey. Collisions occur, and obviously that affects the outcome of the game. Think on a larger scale, like the collision between asteroids and planets that is believed to have played a major role in the formation of the solar system. And of course, think about your safety, like in a car, the collision between two cars. If these things cannot be well understood, then our safety, our entertainment, even the formation of the universe can't really be understood. And so therefore, this is a pretty big topic. In a moment, I'm going to ask you to pause the video and have a look at the kind of questions that we'll be answering here, as well as where we are in the unit schedule and what are the learning goals and success criteria. So please do that now. Okay, and you're back, and we're going to get right into things here with our first slide. First of all, what is momentum? How is it calculated? So this thing called momentum that you've heard about before, it's often described, or at least historically it's been described, as, in a strange way, the quantity of motion is one way that it has been described. And if you're wondering exactly how can it be called the quantity of motion, or what does that mean, take a look on the Wikipedia site, because they'll give you a quick historical overview of momentum, who the major players were, and how the idea was developed, and why it's been given this name here. However, in a moment, I think you'll understand why it's called the quantity of motion. At the moment, just to delay for one more second, you think of motion in terms of maybe this variable, velocity, and meters per second is the units. However, there's more to motion than that, and to give you a hint of where we're going with this, I'd like you to imagine a scenario. Imagine if I gave you a choice. You can be, something's going to crash into you, okay? And your choice is you can be hit by a really heavy thing moving very slowly, or a really light thing moving very rapidly. What would be your choice? And to make it really difficult for you to decide, how about we give you the choice between getting hit by, let's say, a car that someone forgot to put the parking brake on, and it started rolling very, very slowly. So cars are really heavy, but imagine it's just slowly rolling. You can get hit by this, or you could take another option, a really light thing like a bullet, but that's moving very fast. Which one would you choose? Clearly, there's more to motion than just velocity, and I think from the option that I just gave you, or the choice, you can see that the other thing is mass. And these two things go together to create what's called the quantity of motion, or the momentum. In fact, it's a really easy calculation. The momentum is simply equal to the product of mass times velocity. The symbol for momentum is the letter P. It can't be M because we have M for mass. M is mass here, V is velocity. You notice I wrote a vector symbol up here. That's because velocity is a vector. And so yes, momentum is a vector, it's not a scalar. So you will need to include direction when you are calculating momentum. On the next page, I'm going to give you some scenarios, and we're going to calculate or look at the results of some calculations for the momentum of these objects. Although I got to let you know beforehand, I'm going to leave out the direction part of it. I just want to focus on the magnitudes in the beginning. So let's have a look. Here are 5 scenarios. A human walking, humans running the fastest they're capable of running, a high-speed race car, an F1 race car, I guess, as opposed to a slow race car, right? An F1 race car, a bullet coming out of a gun, and an elephant in a room. Well, An elephant in a room standing there wouldn't have much momentum, but elephants, I was surprised to hear this the first time I heard it, they can run quite fast, and so since they're very massive, they can have quite a bit of momentum. Let's look at some calculations. A human walking, 75 kilogram human walking at 2 meters per second, multiply those two out. 75 kilograms times 2 meters per second. Remember, I'm just dealing with the magnitude here. I'm skipping direction for now. You get 150. Here's something interesting, the units of momentum. Kilogram meters per second. I'm afraid this does not collapse into any smaller unit or more manageable unit. Remember with force, where we had F net equals ma, when you've got F net equals ma, you know that a Newton is a kilogram times a meter per second squared. Kilogram meter per second squared is a mouthful. That's given the name Newton. Kilogram meter per second is also a mouthful, but unfortunately no simple unit to use. You just have to say this each time. Kind of annoying. Human running, like in the 100-meter sprint at the Olympics, roughly 10 meters per second is their speed. Same human as the human walking, 750 kilogram meters per second. I think it's safe to say that if I gave you the choice of having one of these two people run into you, you'd prefer to get hit by the walker rather than the runner. The reason is obvious. It's got more momentum. Here's another example, the race car. I looked this up. 650 kilograms is a typical mass for one of these things. They go very fast. They can go up to close to 300 kilometers an hour, which is about 80 meters per second. Multiply these two and you get 52,000 kilogram meters per second. You definitely would rather get hit by this guy with less momentum than by this car with so much more momentum. How about getting shot? That would be terrible. I guess bullets carry a lot of momentum, right? Well, let's have a look. A .45 caliber bullet, mass 25 grams or 0.025 kilograms. Typical speed for one of these bullets is nearly the speed of sound, 300 meters per second. Multiply these two. Here's something strange. Only 7.5 kilogram meters per second. Look at the human walking, 150 kilogram meters per second. Have I led you astray here in getting you to believe that more momentum equals a bigger collision? Well, if that's the case, you should prefer getting shot by a bullet to being hit by a human. Clearly there's more to this than just the momentum value. But clearly there's something about the momentum value because you can see from these three pictures, with increasing momentum comes less desirability to get hit by one of these things. Let's have a look at the elephant here. Typical mass for a large adult elephant, over 5,000 kilograms. And like I said, they can run quite fast. I was surprised to find out they can run at a top speed of about 40 kilometers an hour, which is about 11 meters per second. Multiply these two. You get more kilogram meters per second than you get with the F1 race car. What would you rather get hit by? An F1 race car going 300 kilometers per hour? Imagine if you landed on the track for whatever reason and one of these guys was about to bang into you. Or would you take your chances getting hit by the elephant? I'm pretty sure I'd take my chances with the elephant. I know it wouldn't feel good, but something about 300 kilometers an hour feels even worse to me, or sounds even worse. Clearly there's something more to collisions than just momentum, and we'll find out what that is later in the unit. But for now, you know how to calculate momentum, you know what the units are. It is a vector, even though here we're only talking about the magnitudes. All you do is tack on the vector direction of velocity to the momentum. They're both in the same direction. All right, let's move on. There's another related concept called impulse, and it's related to momentum if we understand how it's related to force and time. So look at this. We start with Newton's second law, F net equals ma. And we know that A is just V2 minus V1 over delta t. That's the definition of acceleration. We expand this bracket, mv2 minus mv1 divided by time. And what are we left with? Well, notice a mass times a velocity is a momentum. This is a p-value. And this one over here is also a p-value. This is the original momentum because it's from the original velocity. This is the final momentum because it's from the final velocity. So what you're left with here is P2 minus P1. But every good science and math student knows that something final minus something initial is just the change or the delta in that value. So look what we got down to. F net, which you used to think of as ma, could also be thought of as the following. F net, the net force acting on an object, is equal to the change in momentum divided by the change in time. In other words, it's nothing more than the rate of change of momentum. Stop and think about this for a minute. Pause the video if you have to. A net force causes a change in the momentum of something. And what it really does is tell you the rate at which an object's momentum changes. A greater net force leads to a greater rate of change in the object's momentum. Pause the video and think about that for a second if you have to. All right, and you're back. An interesting fact is that Newton, when he formulated his second law, actually didn't use this version of F net equals ma. He used this, F net equals delta P over delta T. He framed it in terms of a rate of change of momentum. And for all you calculus students out here, what you'll see is the following. You'll see this written as a derivative, dp by dt. That should look familiar if you've taken calculus. Here's something else that's interesting. Take this formula and rearrange it so that it says delta P equals F net times delta T. Stop and think about this for a minute. If you want to change an object's momentum, how do you do it? Well, we just saw that you have to apply a net force. But how much net force do you have to apply? Well, it really depends on how much time you have available to do the applying of the force. For a given delta P over delta T, you can apply a lot of force for a little bit of time, or you can apply a little bit of force over a long time. Think about that for a minute. Imagine pushing something to get it moving to a certain velocity, to change its momentum. Exert a lot of force, very briefly, or exert a little bit of force, but over more time. What I'm saying here is the following. I could draw this in a sort of diagram. A lot of F net times a little bit of time can give you the same result as a little bit of F net acting for a long time. Here I've used the large letters to indicate large forces, small letters for small time, or the reverse. Small forces for a long time. These can come out equal. We have a name in physics for delta P, the change in momentum. It's also known as, aka, impulse. So if someone asks you to calculate the impulse of an object, it's not like you have to memorize anything new. It's just P2 minus P1. It's the change in momentum that occurs when a net force is acted on that object for a certain amount of time. And the cool thing is now, whenever an object's momentum changes because it's been hit by something, you can now relate how much force is exerted to how much time it was exerted for. Let's take a look at sample problem 2 in the Physics 12 book by Nelson. A baseball of given mass is traveling horizontally to the east at this speed. The baseball bat hits it, and the collision lasts for only about 1,000th of a second, a millisecond. Immediately after the collision, the ball is traveling now to the west, so it's reverse direction, and has a new velocity. So they ask you to do a number of things in this question. We're just going to kind of try to tackle this, maybe not in the order that they asked for, but in our own sort of order. Let's calculate P1. That would be the mass of the ball times its initial velocity. So sub in 0.152 kilograms times the velocity, 37.5 meters per second, but this is to the east. Now calculate the final velocity. That's going to be 0.152 meters per kilograms, but now times the 49.5 meters per second, but to the west. If we want to calculate the change in momentum, delta P, the impulse, then we do P2 minus P1, which is going to be this number, which I'm going to leave it to you to calculate, minus this number, which I'm also going to leave to you to calculate. However, before you do this calculation, take note. One direction is west, the other is east. You cannot subtract these right away. You're going to have to change one of them into the other by incorporating a negative. So maybe make this east into a negative west, and be sure to use that negative when you put it in P1. So there's going to be the negative from the delta and also a negative from making these directions compatible. Once you calculate this, you'll have what's called the impulse. And now they've told you that the time of impact for the baseball bat on the ball is just 1.15 seconds. So what is that in, well, I'm going to write it in scientific notation actually. It's 1.15 milli. Everyone knows milli because it's like millimeters, it's thousandths, right? That's 10 to the negative 3 seconds. You've got to know your metric prefixes, otherwise you're in big trouble here. You know the time, you know the impulse rather, so calculate F net. What is the net force exerted? Well, it's the delta P value that you calculated over here. So get that out and sub it in to the numerator and divide it by the time, which of course is down here. Just make sure you're in seconds. And you're going to get a certain number of kilogram meters per second in the numerator divided by seconds, which is going to give you kilogram meters per second squared, which are newtons. Isn't that what we were calculating? Sure it is, F net. So now we have a way of figuring out how long a force has to be in contact with an object to change its momentum by a certain amount. Or, if we know how much the momentum changed, and we know how long the contact was, we can figure out how much force was exerted. So if you've ever wondered, what is the force of, let's say, someone punching you, or maybe the force of someone bumping into you, then you can relate that in terms of how your momentum changed and how long the contact of the punch or the hit lasted. Let's have a look at how this applies to real life. Here's a guy that has jumped up in the air. He looks way too happy. There must be something wrong with him. However, he is jumping in the air. He's going to land in a moment. Now, let me ask you a question. When you land, what do you instinctively do with your knees? Of course, if you're like this guy way up in the air, you definitely bend your knees when you land. Because if you don't, you get this horrible feeling of pain, a force right up your spine, which can actually cause a lot of damage. Why do we do this? And how do we know to do it? Well, think about the momentum and impulse equation. Think about this. F net equals delta P over delta T, which of course is equal to P final minus P initial divided by time. Now, for any given person of any given mass, so there we go, M, there's his mass, mv2 here minus mv1 divided by time. So this guy, his mass is constant, so this is not really a factor in this analysis. The v2 and the v1 we're going to be thinking about here is as follows. We know that we bend our knees just before we land. So what I'm talking about is when this guy gets right down to the ground, just before he hits the ground, what is his velocity just before impact? That'll be the v1 as he's coming down. Okay? And what is the v2 going to be? Well, that's going to be 0 when he hits the ground and stops. So that's going to mean that this term here is actually 0, because we're talking about landing. We stop moving. So what this comes down to is negative mv1 over time. That's going to be equal to the net force on this guy. Remember, m is not a factor because it's constant throughout the problem. So here's what's going to happen. For any given jump, his initial velocity, meaning the velocity just before the landing begins, will be constant as well. Because if you jump up, let's say 1.5 feet, 1.5 feet, you're going to come down with a velocity that is the same no matter what. You'll always come down with the same. It's just kinematics and acceleration due to gravity. So for any given jump, this is set. It's constant. The only thing you can control is whether or not you bend your knees. If you don't bend your knees, what's going to happen? Pause the video and think about it for a minute. What's going to happen in terms of the physics? Okay, you're back. And what happens is your delta t, the time over which you stop, is very brief. You will stop suddenly. On the other hand, if you do bend your knees, you will stop over a much longer time interval. So I'm going to draw this as a bigger delta t. In other words, since delta t is in the denominator, by having a longer delta t, you have a larger denominator, and therefore the net force exerted on you by the ground will diminish. That's what makes it safe to land from any sort of height worth speaking of, is that you keep the forces small by increasing the time of impact. There's other examples of this too, especially in contact sports, where people can get injured very easily if they don't know how to get hit. Think about hockey players, think about football players, think about boxers. They get hit a lot, yet they keep coming back and they seem fine. Of course, they are very tough, but they're also very smart about how they get hit. See if you can analyze how those athletes get hit and don't get injured in most of the instances. It's got something to do with why we bend our knees when we land. What I think is very interesting here, just on a personal note, is how this is all physics, yet everyone from childhood knows to do this. Like, no one ever jumps without bending their knees. It's not like we all jumped once and kept our legs straight and realized this is a bad idea, it's painful, I'll bend my knees from now on. Somehow we know about it. There's a certain psychology, a developmental psychology going on in our brain where we instinctively know to do that. And if that kind of thing interests you, why the brain knows to do certain things without ever having been taught, then you might be interested in a career in psychology. Check that out. Anyway, we're going to finish off with a new kind of graph that can help us calculate momentum. It's called a force time graph, and before we get to that, I want to show you a really cool video that I found on YouTube. Here it is. It's a golf ball that's about to be hit by the driver. That's the largest club in a golfer's bag, and this is the one you use at the start of a hole where you really want to hit the ball as far as you can. And this is being filmed in slow motion, as the title of the video suggests. I want you to watch what happens to the golf ball at the moment of impact. It happens pretty quickly, so watch carefully, and if you need to, go to this YouTube video and watch it again. Watch this. Did you see what happened? The ball actually compressed. You can see it right there. The ball has flattened out a bit. And it happened so quickly I missed it, so we'll watch it one more time. You could see that impact as the ball sort of squished and then sprung back off. Does this remind you of something that we just finished studying? I hope the answer is yes. It should remind you of elastic potential energy. The idea that when you hit a golf ball, you are actually exerting a force that compresses it. And just like a spring that compresses, the more the compression, the more the force. So if we plot the force exerted on the ball, which is the net force in this case, as a function of time, here's what we find. The force rises until the ball is maximally compressed. And then the ball springs off of the club, the head of the club, and therefore the force goes down, like this. So we have a force time graph that looks something like this. Well, if you calculate the area underneath this graph, you will be calculating base times height, seconds times newtons. Think of the impulse equation again. F net equals delta P over delta T. When you rearrange that to get F net delta T equals delta P, the impulse, look what you're doing. Newtons times seconds. That's impulse. So even though impulse is delta P, which is a change in kilogram meters per second, another way of expressing that is Newton seconds, newtons times seconds, not newtons per second, Newton seconds. That's also impulse, the area beneath one of these graphs. And of course, anytime forces are not constant, you need to use the area beneath the graph. And there are some examples in the textbook, and that is all I have for you today. You're probably wondering, where's the fact of the video? Well, the fact of the video is actually right here with our new version of Newton's second law. I want you to remember this is the fact of the video, that F net is delta P over delta T. Or if you're the calculus type, you can go back to what I showed you earlier, which is that Newton actually had F net written as a derivative. That's the fact of the day. Your choice whether you want it to be dP over dt for you calculus students, or delta P over delta T. That is the fact, and I will see you in class. Thanks for watching. Have a great day.